Hello, welcome to my coronavirus classroom. I'm Janessa Jacobs, and this is the central nervous system. Today we're going to start with our bone of the day, and we're actually going to look at two bones of the day, the bones of the leg. So last time we met the femur, or the long bone of the thigh, and today we're going to meet the bones that articulate with it to form the leg. They are called the tibia and the fibula. So I don't want to hear you say tibula or fibia, because that's not it. It's tibia and fibula. You need to be able to identify left versus right for the tibia, but not for the fibula. So the tibia is the bone that's actually going to bear weight in your leg. The fibula does not. And so, all right, well, how am I going to determine left versus right on this tibia thing? Well, if we look for markings, the medial and lateral condyles are going to be these nice articulating surfaces that are going to articulate with the femur. So that's how those two bones come together. So those are going to go anterior, those are going to go superior. And then I have to find another marking and determine whether it's going lateral or medial. So if we look, our medial and lateral condyle we already met. The next thing is the tibial tuberosity. All right, well, we'll look at that in a minute. Or we can look at that now. It's this enlarged bump here. That's going to go anterior. Okay, this is the shaft. And then medial malleolus. We'll see that the fibula has a lateral malleolus. These malleoli are the things that kind of feel like your ankle bones on the distal portion of your leg. So this is the medial malleolus and this is the lateral malleolus. So how I determine whether or not I'm looking at a left or a right tibia is by putting this tibial tuberosity anterior with my condyles superior, and this kind of pointy part down here on the distal end has to go medial. So this is a left tibia, and this is actually real bone. This is a right tibia. So again, here are my medial and lateral condyles, my tibial tuberosity, my shaft, and then this enlarged region here that kind of feels like your ankle bone. If people are getting ankle tattoos, then that's where they're getting them, is on their little malleoli of the tibia and fibula. So Kelly here is holding up their legs so that we can see the articulations of these bones here. So what you'll notice is that this is the tibia. It's articulating with the femur here. The fibula sits up right next to it. This is the medial malleolus. So if we look at this model of a bone, here's our right. So there's the medial malleolus here, goes medially, and the tibial tuberosity is anterior. So this is my right and my left tibia. And this is how they would look in the body. What's cool about seeing a model versus a real bone is that this real bone has had some of this compact bone on the surface worn away. So if you look here, this is the model, this is the real bone, and here where we have total compact bone intact, you can't really tell them apart, but the compact bone wears off on a real bone at the epiphyses, and you can see the spongy bone in there. And so it's called spongy bone because those little subunits are called trabeculae, and they make it look like a sponge in there. So what's cool about spongy bone is that it lightens the weight of the bone without compromising strength, because we can still pack compact bone on the outside of it and get all of the strength that osseous tissue has to provide. Pretty awesome. Okay, so that's your tibia. So how you're going to determine left or right is you're going to find that medial malleolus and make sure it's medial. Okay, but you could say, well, what if it's, how can I tell? What if it's sitting there like this? So I just flipped this, and what you can see now is I don't see my tibial tuberosity, right? So on the posterior surface, so if I see my tibial tuberosity and my medial malleolus, I know I'm looking at a left one. If I don't see that tibial tuberosity and I see this medial malleolus in that orientation, then I'm looking at a right one. Okay, so the fibula, you only need to know the head, the shaft, and the lateral malleolus. And so the lateral malleolus is the, again, kind of the rounded part that feels like the outside ankle bone here. So if you were to get like, you know, a heart mom tattoo on your ankle, they would be tattooing on the lateral aspect of your ankle. They would be tattooing right there on your lateral malleolus. Your actual ankle bones, the tarsals, are down in here. So what feels like what lay people call the ankle would be your medial and lateral malleolus. So if we look then, we can find the lateral malleolus is this kind of enlarged region here, and that goes distally. This is the shaft, and then this kind of pointy process up here has the head. So fibula, you don't have to know left or right, but if there was a marking right here, if it would, you could maybe walk to your computer and look at your lab practical station, and if there was an A right here and it said what marking of what bone is this, you would say this is the head of the fibula. And you'll say, well, lady, how can I tell that that's the head versus that's the head? Because that lateral malleolus is kind of really more pointy. See that? Pointy. And the head is kind of more, I don't know, knobby. And how they articulate in the body, so this is my right tibia and my right fibula, and how they articulate in the body is just like this. So that what happens is that all of the weight from the femur is going to come onto the tibia, and then the fibula is articulating up here, not really taking any weight onto it. So, all right, those are our bones of the day. How about our muscles? So last time we met the muscles on the anterior compartment of the thigh. So let's go ahead and talk about the muscles that we find on the posterior compartment of the thigh. These are collectively called hamstrings, and these are all going to act as thigh extensors and leg flexors. So our quadriceps were leg extensors and put us in this position with an extended leg. If I were to flex my leg and decrease this angle here, the muscles that are going to do that are the hamstrings. This group of muscles we're going to talk about today, they can also help with extension of the thigh. So remember we said that rectus femoris helped with some thigh flexion. So if I'm flexed at the thigh, then my hamstrings can also help with thigh extension. Okay, and we've got 3 hamstrings. The biceps femoris is the most lateral member of the group, and it attaches here on the most lateral surface. And then the other 2 are semitendinosus and semimembranosus. I always like to use little mnemonics or whatever they're called to help me remember things. And semimembranosus has the most medial attachment, which is kind of weird because you have to kind of look really medial to see it. But you can see semimembranosus is right here, and it's attaching very medially. Semitendinosus is right on top of it. Semimembranosus is actually big and deep to semitendinosus. So like if you were going to be tested on semimembranosus, a lot of times like, you know, you might see a marker here. But a marker here is good. Both of these are that you can see on either side of semitendinosus is semimembranosus. Semimembranosus, most medial. Biceps femoris, most lateral. Semitendinosus right here. So these 3 muscles are the hamstrings, and those are leg flexors and thigh extensors. Okay, so let's do our muscle meditation. Close your eyes, and we'll breathe in biceps femoris, and breathe out, extends thigh, flexes leg, and breathe in semitendinosus, and breathe out, extends thigh, flexes leg, and breathe in semimembranosus, and breathe out, extends thigh, flexes leg, and breathe in biceps femoris, and breathe out, extends thigh, flexes leg, and breathe in semitendinosus, and breathe out, extends thigh, flexes leg, and breathe in semimembranosus, and breathe out, extends thigh, flexes leg, and breathe in hamstrings, And breathe out, extend thigh, flex leg. And breathe in, and breathe out, and come back to class. Okay, so I believe this is going to be the most challenging lecture of the semester to give from my living room. And I say that because the original lecture was 113 slides long, and it is now down to like 61 or 63. So over half of the slides are pictures because you need to see what's going on in the central nervous system to really understand what's going on as we talk about it. So I've got all my models here, and it's gonna be a little chaotic, but I mean, it's gonna work, right? We'll just call it lab credit. I'm gonna use that all semester. Anytime I'm being hard or whatever, we're just calling it lab credit. Okay, so the brain is divided into kind of 4 basic regions. And each of these regions has subregions, but let's first talk about our general divisions. The second reason that this will be the most complicated lecture to deliver from my living room is that this young gentleman has woken up from his nap a tad early, but we're gonna send him and his sissy out to do some camping errands. So before they go, he's gonna help us make a video. And we're gonna look at our 4 brain regions. So what most people think of as the brain is just one part of the brain, the cerebral hemispheres. So these are split into lobes, we'll talk about in a moment, but we can see that we've got a left and a right cerebral hemisphere, and that forms the bulk of the brain for sure. But that's only one of the 4 brain regions. Do you see the hemispheres? Can you hold that model up? Hold it, I'm letting go. Okay, the second region is the diencephalon. And this model has 2 regions, the brainstem and the diencephalon. So I'm going to show you it on its own, and then we'll look in the brain to see the rest of it. So these are the thalami, one thalamus here, the hypothalamus and the epithalamus back here all form the diencephalon. So that's the second portion of the brain. Can we split this open and show them in here? So if you look deep to the cerebral hemispheres is where we can see the diencephalon. Oh, here it comes.
He's gonna.
Oh.
Kara's gonna laugh.
Yeah. Okay.
There you go, there you go, there you go, there you go, there you go.
Okay. So here you can see it still attached, but here we can pull it out. And this is actually pulling out the other 3 brain regions. The diencephalon here, here's the thalamus, which comes through here. Here's the hypothalamus, the epithalamus back here. So that's the second brain region that's deep to our cerebral hemispheres. Can you hold, you got it? Got it. And then next, we have our brainstem, which is inferior to the diencephalon. So that's right here. There are 3 parts, the midbrain, the pons, and the medulla oblongata that leads then into the spinal cord. So brainstem here. Where can we see it on our other model? That's down here. So the diencephalon is superior, the brainstem is inferior, leading into the spinal cord. And then the last part of the brain, here, is on here. Switch ya, hold this one, is the cerebellum. It's like a mini brain, cerebellum, and that hangs off the inferior aspect of the brain. You can see that right here.
You're forgetting these holes in these.
Yeah, those are the ventricles. So it's the inferior and posterior aspect back here is the cerebellum. So those are our 4 brain regions, and we're going to look at all of the specific parts of each of those and what they all do in greater detail in just a moment.
Mom, do you know I could jump off this ladder?
Show everybody. 1, 2, 3, go. Nice, it's done. Those are the 4 main brain regions. Now let's look at how we divide all of those up. First, let's see if you remember something from our last chapter. Axons of neurons run in blank in the central nervous system. A, nerves. B, tracts. C, ganglia. Or D, all of the above. All right, in the central nervous system, axons run in tracts. Why does that matter? Because we're in chapter 12, the central nervous system, which is the brain and the spinal cord. So for your last exam, we talked about nervous tissue in chapter 11. Now we're talking about the organs that are made of nervous tissue. And then this is our control system. So we'll get into our other systems that are controlled by this system. It's pretty great. All right, let's see here. All right, so when we think about the nervous system, we are going to think about our axons of our neurons, and then our somas and the dendrites, and where we find those in the central nervous system and in the peripheral nervous system. And we divide those up, kind of the parts, into what they look like. Are they gray matter or are they white matter? And what is this stuff? What's the distribution of gray and white matter in the brain? So, well, in the nervous system for that matter. So let's talk about that. Gray matter kind of looks gray, and it is where we find the somas of our neurons and unmyelinated axons. So gray matter is somas and unmyelinated axons. White matter is white because myelin is white, so these are our myelinated axons. Okay, and so we will see that the distribution of gray and white matter changes as you move from inferior to superior in the central nervous system. If you look at the spinal cord, what we see is that we've got these kind of central clusters of gray matter, and then this kind of superficial white matter. So in the spinal cord, we've got deep gray matter and superficial white matter. How does this relate to what I asked you in the last question? Axons of neurons run in what in the CNS? They run in tracts. So this white matter that we find here is myelinated axons, and these are running ascending and descending tracts of neurons that are bringing information to and from the brain. So pretty cool. Okay, then what about when we get to the brainstem? The brainstem is kind of weird because in here we have like just random like clusters of gray matter. What are clusters of gray matter, or what are somas found together in the central nervous system? Nuclei, which is weird. We said that somas were found in ganglia in the peripheral nervous system. We could see those outside the vertebral column. We'll look at those again. But nuclei, that's like a nucleus. Yeah, you find somas in like a hypothalamic nucleus. What? Yeah, so it's kind of weird. In the central nervous system, then you find these little bits of gray matter scattered throughout the brainstem, and these little nuclei and kind of white matter throughout it. So what we could say for the distribution of gray and white matter in the brainstem is that we've got gray scattered throughout the white. And then when we ascend up to the brain, now we have a flip where our gray matter is superficial to our deep white matter, and then you have clusters of nuclei or clusters of gray matter deep to that. So when we get to the cerebrum, we have superficial gray matter. We've got deep white matter with clusters of gray matter called nuclei. Okay, so that's the distribution of gray and white matter. It flips. In the spinal cord, we have superficial white matter and deep gray matter. When we get all the way to the cerebrum, we have superficial gray matter and deep white matter. We will talk more about all of this stuff as we move throughout the system. So that's that. Blank cells line fluid-filled spaces in the central nervous system. You should recall from your last exam that ependymal cells line fluid-filled spaces in the central nervous system, and I bring them up now because if we're looking at the central nervous system, in the brain the fluid-filled spaces are the brain, and in the spinal cord we have the central canal. The cerebrospinal fluid also circulates around the brain and around the spinal cord, but in the brain we have ventricles. And I showed you this model when we were talking about ependymal cells for a moment. These are the ventricles, or this is a model of the ventricles. These fluid-filled spaces that contain cerebrospinal fluid. This gives buoyancy to the brain and allows it to float. So, ventricles, I could stick that model back in there. It's beautiful. These fluid-filled spaces in the brain. And these regions in here that have pink have those ependymal cells. Well, the entire ventricles are lined with ependymal cells, but in the pink region, we are free of blood-brain barrier. So the ependymal cells there in these regions called the choroid plexus can pull what they need to out of blood to concentrate it into cerebrospinal fluid, which is going to circulate through the ventricles of the brain and the central canal of the spinal cord, and then around the brain and the spinal cord as well, so that the brain can then float in your head instead of sinking through the foramen magnum, which is the big hole in your occipital bone. Okay, so ventricles. We have 4 ventricles, a left and a right lateral ventricle. So you can't tell me that this is like the first and second ventricle. It's not. It's the left and right lateral ventricle, and then our third ventricle and our fourth ventricle. And our lateral ventricles are connected to our third ventricle by this thing called the interventricular foramen, and then to the third to the fourth by the cerebral aqueduct. So what the heck am I talking about? Okay, left and right lateral ventricles. This right here is the third ventricle. It's kind of weird. Foramen is usually a hole in a bone. But here in the ventricles, these little lateral ventricles are connected to the third ventricle by the interventricular foramen. So then we're looking at the third ventricle here. This is the cerebral aqueduct. And that leads into the fourth ventricle here. And that's going to be continuous with the central canal of the spinal cord. Okay, so what do we have to say about this? Our ventricles contain CSF. They're lined with ependymal cells. We're going to talk about the functions of cerebrospinal fluid later, which is to give the brain buoyancy. But if you want to write it down, you can. I'm not writing it down. Lateral ventricles. We have a left and a right lateral ventricle, and they're going to be connected to the third ventricle by the structure called the interventricular, between ventricles, interventricular foramen is going to lead to our third ventricle, and then our third ventricle is going to be connected to the fourth ventricle by the cerebral aqueduct. And then the fourth ventricle is going to lead into the central canal of the spinal cord. Cerebrospinal fluid is going to circulate through the ventricles, through the central canal of the spinal cord, around the spinal cord and around the brain, and help to protect that soft tissue from the bony tissue that's giving the most protection, but also help to give the brain specifically buoyancy so that it doesn't sink due to gravity. Okay, so now let's dive into each of these different brain regions. First, let's look at the cerebral hemispheres. So the thing about it is, The cerebral hemispheres are the coolest thing ever. And all of the most important parts of you, everything that you associate with being you, your personality, your decisions, like all of that, your sensory perception, is all happening right here in like 2 millimeters of gray matter. So your cerebral cortex out here, like this very tiny space of gray matter out here, is what holds all of the most important parts of you. All of your consciousness is here in your cerebral hemispheres. It's amazing. I love the brain. Nervous system, probably my favorite. I don't know, it's hard. Yeah, it's pretty great. So cerebral hemispheres, this is going to be hugely important, and we're going to spend a lot of time talking about the lobes of the hemispheres and what they do. Why? Because this is what makes you you. All right, so features. As far as anatomy goes, let's start there. So these raised bumps here are called gyri. This is plural. One is a gyrus. And these are like the bumps or the raised regions. Okay, so we're going to look, well, at really only be focusing on 2 specific gyri, the precentral gyrus and the postcentral gyrus. What am I talking about? Precentral, postcentral. We'll talk about that right now. So the other surface feature, sulci. Sulci are the dips. This is the central sulcus. So the shallow dips in the brain are sulci. One is a sulcus. This is the central sulcus. So when we're looking at like specific gyri, or like this is the precentral gyrus, post-central gyrus, those are really the only specific gyri you need to know, and we'll talk about why when we move through lecture. But yeah, surface features. Bumps, gyri, shallow dips, sulci. Sulci. Or a sulcus is one. And these are the shallow dips. And then we have these large fissures. These are deep grooves. And these we find between the hemispheres and between the cerebrum and the cerebellum. So our longitudinal fissure, the one that's long, is that one right there between our left and right hemispheres. That's the longitudinal fissure there. And then the transverse fissure we find in the transverse plane between the cerebrum and the cerebellum. Okay, so cool. We'll talk more. Will we talk more about those? I'll just write them down. The 2 gyri that you're going to need to know are the pre and post central gyri. Why? Because you need to know the central sulcus. It's really the only one you need to know. And then the fissures are the deep grooves. Between our hemispheres, we have the longitudinal sulcus. And between the cerebrum and the cerebellum, we have the transverse fissure. Okay, so those are the anatomical features that we need to be aware of. Now let's talk about the physiology. And of course, anatomy and physiology always go together. So anatomically, our frontal lobes are going to be the 2 lobes of the brain that we find right behind the frontal bone, which is part of the frontal region. See, you guys get mad because you have to memorize so much terminology like chapter 1, but frontal region is where your frontal bone is and where your frontal lobes are. So you've memorized 3 things with 1 word. I wouldn't complain. All right, I probably did. That's a lie. I do complain. I don't know what I'm talking about. Okay, cerebral hemispheres. Now, we can divide our right and our left hemispheres into different lobes. And really all of your brain is working together all the time, but we can look at specific lobes and see that they are really in control of specific functions. Your frontal lobes, these two lobes up here in the front or anterior aspect of your brain, are really where you're doing all of your higher order processing. So as a brain is maturing, it matures from back to front, and it grows from back to front. All of it is really cool. It's always from back to front. These are the last things to kind of like make their connections and mature, and that's really like where all of your like most adult thinking and highest like problem solving ability comes in. So if we're thinking about functions of the frontal lobes, well, anatomy of the frontal lobes, it's from the central sulcus all the way to the front of the brain. So the central sulcus is going to be the divider. Anterior to the central sulcus are the frontal lobes. So these are anterior to the central sulcus. And really these are functioning in all of our higher order processing. So analysis, problem solving. Your personality is up here in your prefrontal cortex. This is like the last thing to solidify. Like around 25, you have your last major neuronal clipping that like gives you your adult brain. And then after that, it's all just what you choose to do with it. Probably is all along. Okay. So this has our higher order thinking. What do I mean by that? Like if you want to contemplate the universe and the cosmos, that's up here in your frontal lobes. So crickets probably aren't contemplating like higher level analysis, like how could I negotiate with this spider so it didn't eat me? So crickets really don't have highly developed frontal lobes, right? So that's what I mean by higher order thinking. The ability to think outside the box. What else? Problem solving. Analysis. So learning language and the ability to understand and like use language starts back here in your brain when you're a little wee one. But really the ability to coordinate all of the motor moves and everything and really understand and read in language is up here in your left frontal lobe. So frontal lobes are also important for that. So really like everything that we think of as like logic, that tends to be in your left frontal lobe. But this is like other things for frontal lobes like language, the ability to use it as opposed to just understand it. All of that stuff is up there. So really personality, we should put up here, that's huge. Another huge function of the frontal lobes is this red line right here is the precentral gyrus. And this is where you initiate all of your voluntary motor commands. So my tracing of this red line with my finger is originating in my precentral gyrus of my frontal lobes. So the frontal lobes also initiate voluntary motor commands. Okay. Next lobe, posterior to that central sulcus, we have our parietal lobes. And so this postcentral gyrus is what we call the primary somatosensory cortex. So your general senses from your body are being processed here in your somatosensory cortex. Your special senses are going all over the place, we'll talk about in a minute. The parietal lobes are posterior from the central sulcus until we get to the occipital lobes. So the parietal lobes back here, and so we'll say this is posterior to our central sulcus and back to the occipital lobes. And really the function of the parietal lobe is it contains our primary somatosensory cortex, which is where general sensory information is first going to come, and then our sensory integration areas or the association areas. So if I want to bring together multifaceted memories and like process all of that information, general sensory information, it's going to be processed here. What do I mean by that? Well, if I'm thinking about like right now, my swamp cooler's not on and I'm getting really hot. So sure, like feeling hot is one thing, but if I start to associate that heat with like, I don't know, what's another general sensory I mean the heat coming off my lamp, but that's like photons too, so that's special sensory stuff. So the heat with the like pressure of my board and the feel of the microphone cord hanging down my back. If all of those pieces of general sensory information are going to be composing a memory, all of that stuff is going to be handled in the other association areas. So the parietal lobe's big function is to help with acting as our primary somatosensory cortex, but also associating all of those general somatosensory kind of things with the memories that we're forming. So we'll say this contains the primary somatosensory cortex, and we'll say association areas. All right, next we have our temporal lobes. Our temporal lobes are behind the temporal bones. As parietal lobes are behind, underneath the parietal bones. Temporal lobes are over here, and our temporal lobes, they're behind your ear. So I wonder, what might they be associated with? You guessed it, hearing or audition. But the other thing is, the temporal lobes actually contain your primary olfactory cortex, which is your sense of smell. And this is going to get weird because when you look forward at sensory processing and go into chapter 15 for special senses, you'll see that it says the frontal lobes are really involved with olfactory processing. Sure they are if you're trying to distinguish smells, but just being aware that you're smelling is happening in the temporal lobe. Be aware of that. Your primary olfactory cortex, or the first part of your brain that's aware that you're smelling something, is in your temporal lobes. So for our temporal lobes, this is the spot kind of behind your ear. It's deep to the temporal bone. And the functions for our temporal lobes is that they have the primary auditory and olfactory cortices. So primary auditory, which is hearing, I'll put that in parentheses, and primary olfactory, which is smelling, cortices are found there. All right. Then in the most posterior aspect of our brain, we have our occipital lobes. Behind that occipital region, the occipital region is the occipital region because the occipital bone is there protecting the occipital lobes. These green portions right here are the primary visual cortices. So visual information is first coming here, and then our visual association area is up here. So these entire lobes are concerned with one sense, the sense of vision. That's huge. 80% of the sensory receptors in your body are in your eyes. That is insane. And look at this entire cerebrum. We're processing so much over all of the rest of these lobes. We're processing one thing here, vision. It's important to see people. Okay, so for occipital lobes, it's the most kind of posterior aspect of the cerebrum, and it contains our primary visual cortex and our visual association areas. So occipital lobes has the primary visual cortex and our visual association areas. You say, yeah, but the parietal lobes are processing only somatosensory information. And I say, yes, that's true. So sure, you could argue that somatosensory information is just as important as visual information. Look how big my eyeballs are, people. Look how big my body is. My entire body gets this part. My little eyeballs get all of this part. Pretty cool. All right. I don't know. Vision's pretty important. All right, the last lobe is called the insula, and I don't even know if I can see it on my models because it's like, if you look in your book, they show you a like brain fork pulling apart like these regions. If you pull back part of your frontal lobe and parietal lobe and temporal lobe, deep to here is the insula. So let's just see if we can come deep to here and see it on this model. Not very many models show an insula. What's in the insula? Why do I care? Because it's got the primary gustatory cortex. What is that? It's taste. You love taste, people. I know you do. Darn it. Man. So, yeah, I don't know. The insula is like right in there. And I can't show you on the model very well. You can look at a picture in your book. If there's a picture on the lab website, that's fair game. It's definitely fair game for a function. What's the function of the insula? It's the primary gustatory cortex. Gustation is your sense of taste. Now you say, okay, well, why isn't that taste gets its whole own cortex. Why is that not as important as vision? You made this big deal about the occipital lobes. Because the insula is like this big. The occipital lobes are huge. A huge amount of your brain is dedicated to processing what you see. And 80% of your sensory receptors are in your eyeballs. You feel and taste and hear all these other things with the other 20%. Just crazy. I don't know. I have no punchline for that. I'm just always in awe of the body. I hope by the end of this you are too. Motor areas. They're in control of motor output. So really the one that I'm most interested in is the primary motor cortex, which is that precentral gyrus. But you also have a motor speech area. So the ability to speak goes above and beyond your ability to produce sound. So the ability to produce sound comes from vibrating air past your vocal folds. But the ability to speak comes from the ability to control the muscles in your cheeks and lips and tongue. So there's a motor speech area in your left frontal cortex, so just be aware of that. So motor areas are concerned with motor output. They're in the frontal lobes. They tend to be your motor speech area tends to be in your left frontal lobe. We also have the frontal eye field. So you don't really have to think about the movement of your eyes. So it's very important to see, as we just discussed with the relative proportion of your brain that visual processing gets. So to control the motor function of your eyes, you actually have motor eye fields also in the frontal lobe. So motor areas. Your primary motor cortex is what's initiating your voluntary motor control. But we also have a frontal eye field that's controlling the movement of your eyes. We also have a motor speech area that's controlling the movement of everything that's involved in speech. Okay? So kind of put that in your back pocket. I do want to talk to you about a motor homunculus. So look it up, people, homunculus, and you can see it. What it is this map. You can look at it in your book. We have a map of the body on the precentral gyrus that they figured out early on in anatomical studies and brain surgeries. They figured out, well, what does the brain think of the body? And what does the body think of the brain? And what they were able to kind of figure out is, okay, if I poke this area of the precentral gyrus, this guy's gonna start wiggling his hip. Okay, if I poke this area of the precentral gyrus, that chick's gonna start flapping her lips. How'd they figure this out? Because your brain does not have pain receptors. It should not feel pain because it should be protected from that by everything that protects your brain. So when you're undergoing brain surgery, they keep you awake. they may block your ability to form memories of the moment, but you're awake. And so as they poke around on your brain, they could see, oh, well, when I poke right here, the lips move. When I poke right here, the jaw moves. When I poke right here, my hand moves. And so there's actually a map of the body on the precentral gyrus. And this is where I wish I had my figures to show you, because it makes it a lot more potent to see. So, okay, look here. I'm just going to show you. Right here. This little tiny region right here. Hip, trunk, shoulder, arm. That's like what? An inch and a half? Gets that much of the brain. Your wrist, your hand, your fingers get like that much. The same amount for my wrist, my hand, and my fingers get the same amount of brain territory as my hip, my trunk, and my shoulders got. Okay, well, what about my face, my thumb, my neck, my eyebrows, my eyes? Look at how much brain territory that is, people. That's huge. This little tiny part of me gets this much of my brain. This part of me gets this much of my brain. So it's pretty cool. Like, the things that are more important for you to have fine motor control over, like your face and your hands, get more brain territory. So that's pretty cool. Our primary motor cortex is the precentral gyrus, and that's where we're going to initiate all of our voluntary motor commands for our, like, the bulk of our body, with the exception, of our frontal eye field and motor speech area. So that's pretty cool. I don't know. I don't know. I love it. Love the brain. Sensory areas. Well, we've kind of already talked about some sensory areas and when we went over our introduction to the lobes. So just as you have a motor map on your precentral gyrus, you also have a sensory map on your postcentral gyrus. So you can look at the sensory homunculus as well, and you see the same thing, that the more important it is for you to be able to feel a particular part of your body, the more brain territory is dedicated to it. So we can see here, if you look, I want to be able to show you on this model because this is like, it's anatomically accurate. So if you look here, your hip and trunk get this much space in your brain. That is most of your body gets that much space in your brain. Look how much space your arm, hand, fingers, and thumb get. Like, look at that. That's insane. Like 3 times the amount for just this little amount of territory. Why might that be? Well, it's super important that we have fine ability to feel things from our hands. So this is like one of our primary ways of encountering the world. And so it's really important to be able to have a really precise map of that on the brain. So a huge proportion of your brain is dedicated to that. Your face also, same thing. Your eye, your nose, your face, your lips, your teeth, your tongue, get that much of your brain. When all of it, like your hip and your trunk's getting that much, that's crazy. So I recommend Googling, no, don't Google, DuckDuckGo, people. They're not tracking you. I'm not being paid by anybody, but don't use Google. Them and Disney, they're taking over the world. Anyway, I digress. You can look up like a homunculus. You should look up the figure of like the proportional models of it. Artists have done these things, and it's hilarious because you get this like person with whose body's like this big, and they have this huge face and these ginormous hands. Like if you're looking at how much of the brain is dedicated to each particular part of the body, it's pretty interesting. Another thing is like you can look at like 2-point discrimination and tell just how important it is for you to be able to be aware of something. What is 2-point discrimination? It's being able to distinguish between 2 points of stimulus. So what you'll find is that if you are to like take, let's say 2 pins, sewing pins, and put them right next to each other on your finger, you can tell that those are 2 points, like even like if they're really close to each other. But if you put those same 2 pins on your back, they'll be right here and it feels like 1 point. and it'll be right here and it feels like 1 point, and it'll be like here and it feels like 1 point. And it's not until you get to like way far out here that you can tell it's 2 distinct points, because it's so much more important to be aware of the sensory information coming into your hands and motor output going to your hands for that matter than it is for what's going on with your trunk. So let's just dig a little deeper and see what these things have to say. The visual areas are concerned with visual processing, photons of light, and everything that's coming in through your eye. The primary visual cortex is the most kind of posterior tip of the occipital lobe. And this is going to receive visual information from the retinas. The visual association areas are anterior to that. Auditory areas, primary auditory cortex is where? Temporal lobes. So your ear is not only involved in your hearing, it's also involved in your sense of balance. We're not going to talk a whole lot about balance or the vestibule of your ear. We'll talk a little bit about it. But the vestibular cortex, we find at the posterior part of the insula and adjacent to our parietal cortex, and that's helping you have conscious awareness of the position of your head in space. So, yep, that's that. Olfactory cortex we already talked about. The primary olfactory cortex is where? Temporal lobes. Gustatory cortex in the insula. Your visceral sensory area is also in the insula, kind of posterior to your gustatory cortex. And this is what lets you be aware of things like a sick stomach or something like that. So in your cortex, you have all these sensory association areas as well. You can read more about them in your book. Question for you. Blank process somatic sensory information. Postcentral gyri, temporal lobes, occipital lobes, all of the above. Yeah, the answer is the postcentral gyri, and that is because they're in our parietal lobes that are our somatosensory cortices. Okay, the blank process sensory information. A, the postcentral gyri. B, temporal lobes. C, occipital lobes. D, all of the above. This time it's all of the above because I didn't say somatic. Sure, temporal lobes are processing special sensory information, but this isn't specifying, it's just saying sensory information. So general sensory information are postcentral gyri. Special sense of audition and olfaction occurring at the temporal lobes. Special sense of vision is being processed in the occipital lobes. So senses are being processed in all of the above. Okay, so that was our first general consideration about the cerebrum. The next general consideration about the cerebrum is that it displays what we call contralateral control. I'm missing a letter there. Contralateral control. What does this mean? Ipsilateral is the same side. Ipsilateral is the same side. Contralateral is the opposite side. Contralateral, opposite side. And you've probably heard that the left side of your brain controls the right side of your body, and the right side of your brain controls the left side of your body. That is because of this contralateral control feature that we should consider in the cerebrum. And that is true because at some point along the information pathway, we're going to do what's called decussate, or crossover from the ipsilateral to the contralateral side. So what we could say is a general consideration for our central nervous system is that it just exhibits contralateral control, where the right side of the brain controls the left side of the body and vice versa. So where the information crosses over depends on the pathway, but at some point it's going to decussate or cross over from the ipsilateral to the contralateral side, giving us this characteristic of contralateral control. Okay. So then another question for you. To wiggle your left toes, you begin the command in your blank. A, left precentral gyrus. B, right precentral gyrus. C, left Broca's area. D, all of the above. To wiggle your left toes, you begin that command in your right precentral gyrus, because we've got contralateral control, left toes controlled by the right side of the brain, and the precentral gyrus is initiating voluntary motor commands. All right, the next general consideration for the cerebral hemispheres is that they display what's called lateralization, or it seems that in most people, we get one side of the brain controlling one thing and the other side of the brain controlling the other thing. And that allows each hemisphere to kind of be worrying about some things while the other's doing the other, so that we can kind of be focusing on it all, in theory. So what does this mean? Lateralization. Each hemisphere specializes in 90% of the population. So in about 90% of individuals, each hemisphere specializes. What do I mean by that? Well, your left hemisphere is going to be the really in control of language and like reading and logic and math and problem solving. And the right hemisphere is going to be more like visuospatial and artsy and feeling and emotional. So we are two-brained people. We tend to hijack the left brain and let that rule the day. But both are equally important. And so lateralization. In 90% of individuals, each hemisphere specializes, just like I said, where your left brain is going to be really logical. And this is where we're going to see that we've got reading and language and speech and a lot of that. And then our right brain, in most individuals, 90%, is going to be more like visuospatial, artistic, emotional. So you've probably heard of right-brained or left-brained individuals. You can actually be both-brained. Most people tend to specialize this way. And so you say, okay, so then most people are also right-handed. Sure, yes, but in these 90% of individuals who lateralize this way, you might actually have some left-handers. So the lateralization of the brain, like as far as executing functions goes, doesn't necessarily correspond to handedness. So in the remaining 10% of individuals, there's a mix of people who lateralize exactly opposite. So their right brain is controlling language and logic and problem solving and analysis and math and science and all that stuff. And their left brain is doing the art and the poetry and the visuospatial and the feeling. And then there are some people who don't lateralize at all. Everything is happening all over their brains. So yeah, and that again may or may not correspond to handedness. Kind of crazy. So what we could say about the remaining 10% are split between the opposite lateralization or no lateralization. Opposite, or I'm not spelling words right, or no lateralization. Okay, any questions? In the class I'd say that and everybody'd look at me like a deer in headlights. There would be no questions, but it would give me time to erase the board and then process. And then right when I was going to change, somebody might say, oh, I have a question. But maybe not. If you have a question, you're going to post it in the Teacher Helping Students Succeed discussion page. Okay, the last thing that we should consider about the cerebrum is that this is where our conscious behavior comes from, goes to, I don't know, chicken, egg, all of it. Anything that you are conscious of is happening in your cerebrum. There are 3 other parts of your brain, your diencephalon, your brainstem, and your cerebellum. You're not really conscious of that. So anything that you are initiating for conscious behavior or responding to is coming from or going to the cerebrum. And if it doesn't, then you're not conscious of it. So conscious behavior, we'll say, arises in the cerebrum, arises, we'll say, in or from the cerebrum. So when I said like all of who you are is in those 2 millimeters of gray matter, that's true. Like your consciousness is all being processed in your cerebral hemispheres. So if you're consciously executing a voluntary motor command, it's coming from your precentral gyrus. If you're consciously responding to a general somatosensory input, that's coming to your parietal lobe. If you're consciously responding to a photon of light, it's going to your occipital lobe. So your conscious awareness or control of anything is just in those 2 millimeters of gray matter, which is pretty crazy. So conscious behavior arises in or from the cerebrum. So if information doesn't make it to the cerebrum, you're not aware of it. So anything below the cerebrum is subconscious. Anything below the cerebrum is subconscious. Right, so running through the cerebrum then, our neurons are communicating from one lobe to another, or from one hemisphere to another, or from a higher brain region to a lower brain region. And when they're doing that through myelinated axons, we find it in gray matter, and we can find them in association fibers. And association fibers you find in the same hemisphere. So it would be like if I was communicating from like one gyrus to the next or something. So communication from one part of the brain to the next in a specific hemisphere is happening through an association fiber. So these are communicating within the same hemisphere. Then commissural fibers are coming through here and connecting one hemisphere to the next. So this region is called our corpus callosum, and our commissural fibers are going to be how we get from one region to the next. So this communicates, between our hemispheres, communicates between our right and left hemispheres. And then we have projection fibers, and this is when we have neurons shooting information from a higher brain region to a lower brain region. So this communicates between higher and lower brain regions. Okay, awesome. So that's the cerebrum. That is 1/4 of your brain, but it is like the most interesting quarter of your brain. So if we look, this is another model that is like fair game. Here we have our cerebrum. Here are those commissural fibers would be coming through here. Here's the diencephalons in here, brain stems here, cerebellum back there. Okay, I'm sure that the lab assistant will be very useful in assisting you with everything you need to know. All right, so the next portion of your brain is the diencephalon. The diencephalon has 3 regions. The thalamus is going to be kind of our frame of reference. Hypothalamus is below it, and then epithalamus is upon it, but it's kind of like back behind it in us. So the diencephalon has 3 parts. The thalamus is what we're going to use to orient ourselves, and it is the sensory relay station. Well, what do I mean by that? You've got a ton of different sensory information coming in, and your thalamus, all of that information is going to be coming into your thalamus, and your thalamus is going to ship it off to the appropriate part of your cerebrum that needs to deal with it. So the thalamus is the sensory relay station. What does this mean? It ships sensory info to the appropriate lobe for processing. Lobe where? In the cerebrum, of course. The hypothalamus is amazing. I love it. It, as far as like a function, is the master regulator of your autonomic nervous system and your endocrine system. So pretty much like everything that you don't control. You control skeletal muscles. Your hypothalamus controls everything else. Cardiac muscle, smooth muscle, and glands. It's amazing. So its function, we could say, is that it's the master regulator of your autonomic nervous system, which is the ANS, autonomic nervous system, and the endocrine system. So that's the fancy way to tell you about it. The way that's going to make you remember it is to tell you that the hypothalamus is in control of the 4 F's. Fighting, feeding, fleeing, and reproduction. I'm going to let you imagine how that's an F. So the hypothalamus controls the 4 F's. We'll talk a lot more about the autonomic nervous system at the end of this semester, and we'll talk about the endocrine system at the beginning of next semester. So the hypothalamus regulates that. Hypo, below, the thalamus. This thing is so important, but it is just like the most unsuspecting little bit of tissue that you ever did see. So here's the thalamus from the mid-sagittal view. The hypothalamus is like right there. Oh my goodness. Like what? That's the hypothalamus? Yeah. And it does all that important stuff? It sure does. Here's like, look at this. It looks like an orange triangle. That little thing? Oh yeah. Sexual urges, motivational states, fighting, feeding, fleeing, reproduction. Hypothalamus. Next part of the diencephalon. Okay, last is the epithalamus. There are 2 parts. We're really only going to worry about the pineal gland or the pineal body. And what that's in control of is your diurnal cycles or your sleep-wake cycles. So we'll say that this contains the pineal, and this controls your sleep-wake cycles. Where is that? It is right back here. So we'll do a dissection and you'll be able to see this. It's like this little bulb back here. And so what happens with the pineal is that when the sun starts going down, the pineal starts getting activated and it starts secreting melatonin in everyone, diurnal or nocturnal. We're diurnal, we stay awake all day. Nocturnal animals stay awake all night. Either way, everybody's secreting melatonin at night, and that's coming from the pineal gland. All right, so that's the diencephalon. So, diencephalon, thalamus, hypothalamus, epithalamus. Okay, diencephalon. And that's going to lead into our brainstem that has 3 parts. The midbrain here. Crappadocious. All right, brainstem. So, midbrain. Midbrain. Right here. I'm not worried about the corpus quadrigemina and all of that stuff, superior olivary nucleus. Just know if there's an A here and it's asking you what is it, midbrain. What does it do? Audio and visual reflexes. What does that mean? If something's flying past your face and you hear it and you track it, that's controlled in your midbrain, okay? Midbrain, audio or auditory and visual reflexes, okay? Right here, this region, very distinct. Pons. This region right here, medulla oblongata, is gonna lead into your spinal cord. Brainstem, okay? That's your brainstem, midbrain. Auditory and visual reflexes. Reflexes you don't think about, you just do. So if something flies past your face and you track it with your eyes, you're not thinking about it. Controlled in the midbrain. If you hear a sound behind you and you turn to track it, midbrain, you're not thinking about it, that's a reflex. Okay, pons. It adjusts things. So your medulla oblongata actually sets your basic vital signs. So it sets your heart rate. No, that was a lie. Your heart sets your heart rate. If you need to adjust your heart rate, you can do it through the brainstem. But it sets your respiratory rate, and so it's really in control of like your basic vital life signs. If you want to adjust your respiratory rate to do something like sing, then your pons does that. So your pons, we could say a good function of that is it adjusts respiratory rate, makes other adjustments as well. That's the easiest one to track. Medulla oblongata will say sets our vital signs. And so the thing that you can tell about organisms is like how important something is for an organism by how closely related our brains are. And I can tell you lizards have brain stems with a midbrain, a pons, and a medulla oblongata. Sure, they also have a diencephalon. Sure, they also have a cerebrum. But their cerebrum is thinking about like, well, what do you imagine a lizard's cerebrum is thinking about? How can I get that fly the quickest? It's definitely not pondering like, how far away is that star? And what is the impact of its gravitational pull on me? That stuff is all in your cerebrum. So like brainstem, diencephalon, everybody shares that. Everybody needs to be able to fight, flee, feed, and reproduce. Everybody needs to be able to have reflexes to things flying past them. Everybody needs to be able to set your own vital sign. So that's kind of just something to be aware of, that you can tell how kind of complex an organism is by how developed these different brain regions are. And really, we all have pretty similar brain stems. There's not a whole lot to be done as far as like, you know, setting a respiratory rate goes. There is a whole lot to be done if you're trying to solve the problems of the universe. And then in that case, you gotta grow a big cerebrum. All right, so next. Our last brain region is the cerebellum. It's like the mini brain sitting on the posterior and inferior aspect of your brain. It really functions to compare motor output to sensory input. What the heck does that mean? It's making sure that you're doing what it is you want to be doing. So let's say I want to be touching my nose, but instead I am aiming to touch my cheek. My cerebellum should be able to detect that I'm gonna land on my cheek and make the adjustment, so I hit my nose instead. So its function we could think of is to compare output to input and make sure we're doing what we want to be doing. So we'll say it compares motor output to sensory input. It's telling you like about your place in space, so it lets you know about limb position and all of that. When it's functioning, it corrects, it makes a correction. We could say it corrects or adjusts to ensure you're doing what you want to be doing. What does that mean? Well, really we can link this very, very closely to physical stuff. There is a growing body of evidence that the cerebellum is also like comparing input to output for emotional stuff. But right now we can say for sure it's happening with physical stuff. And so how do we know this? How can we test this? How can I make sure that you remember this? Well, the cerebellum is the first thing that's knocked out by alcohol. And so when you are pulled over for a roadside test, what that police officer is testing is whether or not your cerebellum is functioning. And if your cerebellum is functioning and he tells you to walk a straight line while touching your nose, then you'll be able to do it. If your cerebellum isn't functioning when he tells you to walk a straight line and touch your nose, you're going to be walking your straight line, but you're going to be like lining up to hit your cheek. And you're going to have to like really think about it. And he's going to say, oh, that person's cerebellum's not functioning, they're inebriated, maybe I better make them blow a test, take them down to the tank. I don't know what they do. I've never had a roadside test. All right, so we're not even gonna go down that route. I would argue, because I know how the cerebellum works, I could get my cerebrum to override all cerebellar input and inhibition. But I never said that. It was Chip. Anyway, under normal circumstances, the master controller of the autonomic nervous system is A, the cerebrum, B, the hypothalamus, C, the endocrine system, or D, all of the above. All right, yeah, the hypothalamus is the master regulator of the autonomic nervous system. Now, why did I put this word normal here? Well, if your autonomic nervous system is, say, like in a fight or flight situation, like you're panicking because your neighbor just like slammed the door and you got really scared or something, I don't know. And you could, like, okay, as soon as you realize consciously in your cerebrum, there's nothing to be afraid of, you could slow your heart rate, okay? Or if you were to like start experiencing like anxiety and be getting a panic attack, you could close your eyes. You could voluntarily control your breathing rate. Your pons would be helping, your cerebrum would be helping. It would all be working together. So sure, your cerebrum can have an influence on the autonomic nervous system, but not the end-all be-all. Like if your cerebrum, let's say you're like a kid and you're throwing a temper tantrum and your cerebrum is like, Mom, I hate you! I'm gonna hold my breath until I die so you don't have me anymore. The cerebrum is saying, hold your breath until you die. And so you hold your breath. And then you pass the F out and your brainstem takes over and you start breathing again. So yeah, the cerebrum can exert some control, but not all the control. Your hypothalamus is the master regulator of your autonomic nervous system. Okay, next question. A patient is struggling to maintain body temperature after a traumatic brain injury. Which portion of her brain may have been damaged? A, the parietal lobes, B, the thalamus, C, the hypothalamus, or D, all of the above. All right, right now you're saying, lady, we didn't even talk about temperature regulation. We sure did, chapter 1, baby. And we said that the hypothalamus had the thermoregulatory center in the brain. You're bringing it all together right now, people. Even if we didn't say that, the hypothalamus is the master regulator of the autonomic nervous system. The maintenance of your body temperature is something that you do not have to think about. It automatically happens. So your hypothalamus is controlling that. If you can't all of a sudden control body temperature regulation, then there's probably something going on there. So back in chapter 1, we said that the organs in the ventral cavity were surrounded by serous membranes, and the organs in the dorsal cavity were surrounded by meninges that we were going to talk about in greater detail later. Now's later. So here are the meninges. The meninges are the layers of tissue that protect your soft brain from your hard bone, your hard skull, and protect your soft spinal cord from your hard vertebral column. So for the meninges, there are 3 layers. The toughest layer and the most superficial layer is called the dura mater. And look, this is one T here. This is the word mater. It's like Latin for mother. Maybe it's Greek for mother. One of them for mother. It's a dead language, almost assuredly. So dura mater is the strong mother. And this is the strongest layer. And it actually has 2 layers. A periosteal layer, which is the outer layer of dense connective tissue that is in contact with the bone. And this is really helping to kind of protect the soft tissue from that hard tissue. And then we have an intermeningeal layer. And this is also just connective tissue, but it's kind of arranged in a more wispy fashion, connecting to our next layer, the arachnoid matter. or arachnoid mater. And the arachnoid mater gets this because if you look, it's kind of got two parts. The arachnoid mater that's in contact with the dura mater, and then these little wispy, like fibrous connective tissue things that are going through the subarachnoid space and contacting the innermost layer. It looks like a spider web. That's why we call it arachnoid mater. And this is, it's like a thin, fibrous connective tissue. And in this subarachnoid space, we're circulating the cerebrospinal fluid that helps to float the brain. So be aware of that. The innermost layer is called the pia mater, the gentle mother. And this is going to be the layer that's, it's connective tissue, loose fibrous connective tissue that's hugging the brain tightly and dipping into the sulci. And so this is, it's fibrous, but it's connective tissue that tightly, it's kind of this loose arrangement, and it's very soft and thin, that tightly hugs the brain. This is going to bring in the little capillaries that serve the brain tissue. The arachnoid mater is going to bring in the bigger branches of our blood vessels that are serving the brain. So those are the layers of the meninges. And again, the dura mater is this kind of dense layer that's protecting the softer stuff from the bone, and then the pia mater is this soft, kind of delicate, fibery layer that is like hugging the brain tightly. We'll see it on the brain dissection. It's this really kind of glossy, pretty kind of tissue to look at. Another aspect of protection for the brain is cerebrospinal fluid. How does cerebrospinal fluid protect the brain? Well, it gives it buoyancy, so it protects it from gravity, being like pulling on it and pulling it through your foramen magnum, but it also slows the movement of the brain. So if your head banging like a maniac, your brain isn't crashing into your skull at high velocity because cerebrospinal fluid is slowing it down. So cerebrospinal fluid circulates in that subarachnoid space and then also around your brain through the central canal and around your spinal cord. So that's really a huge important function of cerebrospinal fluid, is that it's going to give the brain buoyancy so that it floats. Wow, buoyancy. I don't know. We're third tries the charm. Buoyancy. So it doesn't sink through the foramen magnum. It slows the momentum of the brain. So it helps to prevent trauma, so that your brain doesn't whack into your skull. This helps to control the chemical milieu of our nervous tissue, or the chemical environment. So pretty darn important. Okay, the last kind of protection that we have for the brain is the blood-brain barrier. And this is because of two things. What? The tight junctions that we find between the endothelial cells of our capillaries and the astrocytes reaching out and grabbing around those capillaries. So our blood-brain barrier is going to control the passive passage of materials into the brain, and it's created by those two structures. So because we have tight junctions between our endothelial cells and our astrocytes, and what it's going to do is prevent the passive passage of materials into the brain. Okay, we're almost done. Where it's spinal cord, and I got like food baking in the background and kids grumping, so I think we're gonna take a dinner break and I'll come back for Anatomy After Dark. All right, I didn't make it back to class last night, so it's a new day. We're gonna do a new bone of the day. I am absolutely positive that between this lecture and your next lecture, in a normal class, we would have had 2-3 classes in here. So we're just doing it, we're going with it. And so we're gonna finish our lower limb with the foot. And that's because for your next lecture, I got a foot stuck in my hair. For your next lecture, I want to look at the vertebral column because we're going to be talking about our nerves that come out of the vertebral column. And yeah, so let's get through this. And even though we won't talk about how we attach the lower limb to the trunk yet, we're going to move to the vertebral column for your next lecture so that it all kind of fits together. So, bone of the day for our lower limb, we have the foot. Hopefully you can just look at a foot and tell if this is left or right. What kind of foot do you think that is? It's a right foot. And so in the hand, we said that you could just collectively say that any of these little bones down here were carpals. Most of them down here we could say are tarsals. But you do have to know two specific tarsals, talus and calcaneus. So this big one right here is calcaneus. This is why it's the calcaneal region. And this is talus. Talus takes the weight from your tibia and puts it onto calcaneus. So your tibia sits on top of talus like that, and then talus is on top of calcaneus. And then we have our other tarsals, and then we have our metatarsals and our phalanges that we have in our digits. So just as in the hand, we started our numerals with the metacarpal that went with our pollex, we're going to start with the metatarsal that goes with your hallux. So this is metatarsal I, or 1, Roman numeral 1. This is metatarsal Roman numeral number 2, II. Metatarsal number III, number 3, number IV, number 4, and number V. Roman numeral V, number 5. Metatarsals 1 through 5, and then these are the digits. And again, in the hallux, just as we saw in the pollex, we only have a proximal and a distal phalanx. But in the rest of the digits, mostly, we have a proximal, middle, and a distal phalanx, or proximal, middle, and distal phalanges. Although I did have one student who brought me an x-ray of her foot one day, and she was missing her little middle phalanx on her smallest digit, on digit 5. And so this is kind of the thing that's interesting. There's variability in number of bones in people in just in a couple places. The foot is one, that's one area, and then also down here in the coccyx, you can have like I don't know, 3 to 5 fused vertebrae down here. This used to be our tail. This is our tailbone. So as we evolve, we need fewer bones here. As we have evolved to wear shoes, it's less important that we be able to bend our little toes as much. So maybe it is now that if you, before, back in the day when we didn't wear shoes, if you only had a proximal and a distal phalanx, then maybe you would have a less chance of surviving. So everybody survived who had a middle one, and now we wear shoes, so it's not important that we feel. So that's not a selection marker anymore, and people are sticking around even if they only have 2 phalanges on their little toe. Weird fact, brain break this early in the day. It's actually late in the day, isn't it? Hopefully you're watching this all the way through. Okay, so that's all we need. That is the bone of the day. What about our muscles? All right, let's look at the leg. So we talked about the thigh muscles before. Let's look down in the leg, and let's talk about some more movements. So this is the dorsum of your foot. So if you do dorsiflexion, you pull your toes up toward the dorsum of your foot. Could I dorsiflex right now? Ooh, like that. Okay, so tibialis anterior dorsiflexes the foot. Inversion is when you take this plantar surface and point it medially. So you invert your foot like that. I can't believe I just did that. You all saw the bottom of my naked foot. Invert. You can't even tell that's happening. I'm too short. Here, Kelly, assist us in some inversion here. Okay, so here, oh, getting caught in the mic. If you face the plantar surface of your foot toward the midline, that's inversion, and tibialis anterior is going to help with that. Extensor digitorum longus is, how are we going to know this? So your digits are your toes, and they've got these tendons that are going to attach to this extensor digitorum longus, and when it contracts up here, it's going to pull your toes down there. So to find extensor digitorum longus, we just have to look for that and those tendons and follow it up. So this is extensor digitorum longus, and then this is tibialis anterior. It's anterior and to your tibia, and these are the muscles that we're looking at today. So tibialis anterior is going to be able to contract. The muscles always pull, they never push, so it'll pull up on those tendons and help with dorsiflexion of the foot. It can also pull to help with inversion of the foot, and then our extensor digitorum longus is going to help with dorsiflexion of the foot and extension of the toes. So that's that. And meditate. All right, so close your eyes and breathe in tibialis anterior, and breathe out dorsiflexes and inverts foot. And breathe in tibialis anterior, and breathe out dorsiflexes and inverts foot. And breathe in tibialis anterior, and breathe out dorsiflexes and inverts foot. And breathe in extensor digitorum longus, and breathe out dorsiflexes foot, extends toes. And breathe in extensor digitorum longus, and breathe out dorsiflexes foot, extends toes. And breathe in extensor digitorum longus, and breathe out dorsiflexes foot, extends toes. And breathe in and breathe out, and come back to class. All right, this is my non-artist, I am an artist, but not of spinal cord anatomy. Should do better, but whatever. It's my living room. So spinal cord is the other organ of your central nervous system, and it's going to be bringing information from your peripheral nervous system to your brain, and information from your brain out to your peripheral nervous system. So spinal cord, as far as gross anatomy goes, what could we see with our eyes? It has different portions, and they correspond to the spinal nerves that are coming off of it. So this spinal cord right here, this vertebral column right here, will actually form the basis of our next bone of the day. But as you can see, we have all of these spinal nerves emerging here. And so the part of the spinal cord that the nerves are arising from is like corresponds to the name of the bones and all of that. So like right here, these bones are your cervical vertebrae. This is the cervical part of your spinal, the cervical part of your spinal cord, and cervical nerves are coming out of here. Then in here we have the thoracic vertebrae. This is the thoracic part of your spinal cord. We have thoracic nerves coming out of here. Okay, so as far as our spinal cord goes, what are the different parts? The most anterior part is the cervical part. And it has this cervical enlargement here. And if we look at a cross section of the spinal cord, we'll see that it has this like gray matter, this deep gray matter that has all of our motor neuron somas in it. So we have these enlarged regions of gray matter kind of here anteriorly. So in the spinal cord, we have an enlargement here in the cervical region for more motor somas, because there we have all of the neurons that are going to go out and control the muscles in our arms. So the cervical part has a cervical enlargement. And that we could say is due to an increased number of motor neurons, or I should say motor neuron somas, to serve the arms. Okay. And then we have the thoracic part. And then we have the lumbar part. And now in the lumbar part, we have another enlargement, the lumbar enlargement. And why might we have a lumbar enlargement? Contains all of the somas for the motor neurons that are going to serve the lower limbs. So the lumbar enlargement contains somas for the lower limbs. I should say motor somas, motor neuron somas for the lower limbs. And then just a little bit inferior to that, we see the end of spinal cord proper in what's called this conus medullaris. It looks like a cone down here. It's called conus medullaris, and this is the end of spinal cord proper. So what's going on here? If I look at the cervical part of the spinal cord, it's going to give rise to 8 cervical spinal nerves. If I look at the thoracic part of the spinal cord, it's going to give rise to 12 thoracic spinal nerves. If I look at the lumbar part of the spinal cord, it's going to give rise to 5 lumbar spinal nerves. Now what happens as we move inferior in the spinal cord now to our sacral and coccygeal spinal nerves is that they are going to exit out of here in just their nerves instead of being contained like in the spinal cord here. Spinal cord proper ends and becomes this stringy thing full of neurons called the cauda equina. Cauda equina, horse's tail. It looks like a horse's tail. So after conus medullaris, the end of spinal cord proper, all of the rest of our spinal nerves are 5 sacral spinal nerves and 1 coccygeal spinal nerve. They're all going to exit spinal cord proper kind of at that, it ends up there superior, and then all of the spinal nerves will come out inferior to that. Let me see if I can show you what we're talking about. So you can see we've got our cervical nerves, our thoracic nerves, our lumbar nerves. Can we see conus medullaris in there? Not really, but if you look zoomed in there, you can see that instead of being nice and encased in spinal cord proper, when we get down to the cauda equina, all of those spinal nerves are coming out in these long strands that you can then see are emerging through those sacral foramen. Okay. All right. So at this conus medullaris then, coming off of this kind of cone-shaped region, you see your lumbar and your sacral nerve roots are going to pop off of there and kind of branch into this cauda equina. So if we're thinking about all of the things that are going to anchor this structure in the vertebral column, on the superior aspect, the spinal cord is anchored to the brainstem. So superiorly, we're anchored to the brainstem. Inferiorly, what we would see coming out of this conus medullaris and extending all the way down through the vertebral column and attaching to the coccyx down here is this strand of kind of extension of pia mater called the filum terminale. And it's going to go down and anchor the spinal cord inferiorly to the coccyx. So I will write that. So we could say this is called the filum terminale. And this is an extension of pia mater that anchors the spinal cord inferiorly. All right, well, what about all of these? How can we like keep it anchored laterally? We have all of these spinal nerves exiting here, and they're attached to our spinal cord. They've got these things called denticulate ligaments that help to kind of anchor them laterally. So those are also extensions of pia mater, denticulate ligaments, and they help to anchor laterally. I think that's the most important stuff from the gross anatomy of the spinal cord. We do need to talk about the cross-sectional anatomy, but I think that'll be better with a model than a picture. Okay, so actually maybe we need both. So here's the picture that I drew you. Is corresponding to the model in this way. So if we look at the spinal cord, we said that in the spinal cord, our gray matter is deep to our white matter. And our white matter then is going to have these tracts of myelinated neurons that are ascending and descending the spinal cord to bring information to and from the brain. Right here then we have all of this gray matter. So these are somas of sensory neurons and motor neurons and unmyelinated interneurons. So what we can see here is that these are called, they get different anatomical names. These are the ventral horns, lateral horns, and dorsal horns. And those are just these arrangements of gray matter here in the spinal cord. And what we can see is that back here, here's a spinal nerve, which is our next chapter. Nerves are part of the peripheral nervous system. But our spinal nerves are exiting the spinal cord. So our spinal cord has information in here that's coming into here. And right here, these were those ganglia that we talked about in chapter 11. The groups of cell bodies outside the central nervous system are found here in ganglia. So these are our unipolar sensory neurons, and they're bringing sensory information into the spinal cord. So right here outside the spinal cord, I can separate the information in a nerve, and I can see this is sensory information, and these neurons are coming into synapse in here onto the somas of interneurons, or maybe directly onto the soma of a motor neuron in the case of some reflex arcs. So that's what we have going on here. Then here, our lateral horns have autonomic motor cell bodies that we'll see going out through our thoracic nerves to control all of your viscera. And then your somatic motor cell, which is what you control, motor cell bodies. Okay, so what we see is that we have general sensory information then coming along this posterior aspect and synapsing then in those posterior horns. Our motor commands, both for our autonomic nervous system, which is originating, the somas are in the lateral horn, and then the axons are extending more anteriorly and shooting out through something else we'll talk about at the end of the semester. But our voluntary or somatic motor neurons have their cell bodies here, like more in the ventral horn, or the ventral root, the ventral horn, and then their axons are extending through the ventral root. So if you look here, these are called spinal nerve roots. This is the ventral root, this is the dorsal root. Dorsal root, ganglion, has the somas of our unipolar sensory neurons. So we can always tell dorsal from ventral by that ganglion, or posterior from anterior by that ganglion. So in this ventral root, we're only carrying motor information. Either way, that's next chapter. It relates to the spinal cord and the central nervous system in this way. Our sensory, both the senses that we're aware of and our general visceral sensory information is all coming back in here and synapsing onto interneurons here in this dorsal horn. Our somas of our motor neurons are starting in the lateral and, did I just say that backwards? Our somas, I'm gonna have to listen to this when I edit it. Somas of our sensory neurons are originating here, and they're synapsing onto interneurons back here in our dorsal horn. Or motor neurons. And then our motor neurons have their somas here in the lateral and ventral horns and are extending their axons away in ventral roots. So right here we could separate the information. When we get to a spinal nerve, you can't. We'll talk more about that next chapter, but that's kind of the arrangement here. This little hole in the middle is called the central canal. That's where we will be circulating our cerebrospinal fluid in there, and then also around the spinal cord. Other things to be aware of. We call these tracts, ascending and descending tracts. I told you about all the names of our gray matter. The layers of the meninges. The spinal cord is also protected by meninges. So you've got your dura mater is the most superficial. If you've ever had an epidural, they go in and then right on top of the dural mater, they drop anesthetics that deaden the nerves from there down. And then we have our arachnoid matter still, and then the pia mater tightly hugs the spinal cord, and then also extends out is those denticulate ligaments, which we would see extending through here, and then down through the filum terminale inferiorly. All right, that is the anatomy of the spinal cord. Oh my goodness. Look at this. Alex has a great demonstration of our spinal cord that I should have brought out in spinal cord lecture. But alas, here it is. So cervical enlargement. And then we come down and there's our thoracic spine, right? And you can see over here that we would have these denticulate ligaments, which are helping to stabilize laterally. This is great. It's leading out into our spinal nerves that we're about to talk about. So yeah, spinal cord. And then out here, we've got our different layers of meninges that are protecting it. Oh, you can see our arrangement of our gray and white matter as it relates to the spinal cord. And then as you come down in here, this would be your meninges again, leading down into our conus medullaris. This is the end of spinal cord proper. So we have the lumbar enlargement right here that is going to give rise to the somas of the motor neurons that are then going to extend through our lumbar nerves out to serve our legs. And then we've got our sacral nerves come out through here, and our one coccygeal comes out through here. So down here is all that cauda equina part that kind of looks like a horse's tail. So that is the gross anatomy of the spinal cord from the Alex perspective. We'll go over it. I don't think you have a spinal cord lab, but for lecture you sure did talk about the spinal cord, and the figure in your book that I'm not copyright infringing is showing you this perspective here where you can see your cervical spinal cord, cervical enlargement, thoracic spinal cord, lumbar spinal cord, a lumbar enlargement, conus medullaris, our cauda equina, or the horse's tail, and this is where you'd have that filum terminale extending down and anchoring your spinal cord to the coccyx down there. And that's your coccyx down there, so that the spinal cord is anchored inferiorly by the filum terminale to the coccyx, and it's anchored superiorly to the brainstem. All right, so spinal cord physiology is pretty complex. So you can go into all of the nitty-gritty details of ascending and descending pathways in a neurophysiology class. We're going to go over the basics, talk about what ascending and descending pathways are, talk about the general rules that apply to neuronal pathways, and then we'll be done with this chapter. Okay, so one of the things that we can say is a general thing to consider about neuronal pathways, or the pathway that information is following through neurons is that we have three things to be aware of. They're going to decussate at somewhere along the pathway, meaning that the information is going to cross over from the ipsilateral to the contralateral side. We're going to have relay, where one neuron is passing the message off to the next, to the next, to the next, like batons in a relay race. And then we have symmetry, where if we've got one neuronal pathway on the left side of the body, it's symmetrically mapped out on the right side of the body. So, all right, neuronal pathways, they all decussate. This means that somewhere along the transmission of information, we're crossing over from the left side to the right side, and that's what gives us that contralateral control. So decussation in a neuronal pathway is somewhere in the pathway, the information crosses from the ipsilateral side to the contralateral side. So I'll say somewhere in the pathway, information crosses from ipsa to contralateral. Okay. That might happen at the level of the spinal cord that the information is coming in at, or it might happen in the brainstem. It depends on which type of sensory receptor you're activating. The other thing to be aware of is that neuronal pathways act in a relay-like fashion. So you've seen relay races where the first runner runs the baton to the second runner and hands it off, runs the baton to the third runner and hands it off. That's how it works. We're going to conduct action potentials from one neuron to the next in a relay-like fashion. So we could say nerve impulses or action potentials are conducted to and from the brain in a relay-like fashion. And then the last thing to be aware of is that we display symmetry. So if we have a neuronal pathway on the left side of the body, there's a symmetric neuronal pathway on the right side of the body. So we'll say neural pathways are symmetrically mapped on left and right sides of the body. Neuronal pathways are symmetrically mapped on left and right. So this is all the stuff that I'm erasing because my camera doesn't beep when the card runs out. The next time I go push play or pause or whatever, it beeps then. But what if I have talked for 45 minutes? It wasn't 45 minutes this time, it was only like 15. These are the joys and, I don't know, curses of teaching from your living room. Here we go. You lost your sum up of the last thing, but you probably didn't want it. Like you yacked too much already, lady. So let's talk about tracts. Tracts of neurons are axons of neurons running together where? The central nervous system, right? So tracts. These are axons of neurons running together in the CNS. Does anybody remember what axons of neurons run in the PNS? Nerves, you got it. All right, so tracts. These are going to be the ways that we get information to the brain or from the brain so that we can maintain homeostasis. So if you see next, we're going to descending. So we have ascending tracts that are bringing sensory information up and descending tracts that are bringing efferent commands out. So this is where we get that kind of relay thing from. That in all of our tracts, we have one neuron that passes the message to the next neuron that passes the message to the next neuron, and we can tell you exactly where each of these neurons are and where they're passing these signals to from place to place to place in the body. So our first order neuron is the neuron that's talking to the receptor. So we've got some sensory receptor, either a visceral sensory receptor or a somatic sensory receptor, something that's happening in our guts we're unaware of, or something that's happening that we are aware of. Either way, the receptor is going to detect stimuli, right? Changes in variables. And it has to tell this to someone, and the someone is a first order neuron. And in the case of our somatic sensory information, this is going to be a unipolar neuron who has its soma in that ganglion that we said was an organ of the PNS. So if we look at this model, just outside the vertebral column, you can see this little enlarged region. That's the ganglion, and it's enlarged because it's got all these somas of our unipolar sensory neurons. Wait a minute, this is our first order neuron. Well, we said we could classify all of our neurons based on anatomy and physiology. We do that with everything, anatomy and physiology, that's where we're at. So our first order neuron is like the first runner in the relay race, and it is a sensory neuron by its functional classification. And in the case of our somatic senses, our general senses from our body, it is a unipolar neuron by its anatomical classification or its structural classification. So this is going to be the one. Its job is to bring information from the sensory receptor to the central nervous system. So it brings afferent, we could say, information from the receptor to the central nervous system. And in this case, we're talking about the spinal cord. So the central nervous system that we're coming to is the spinal cord. And the second order neuron that we're synapsing onto is an interneuron in the spinal cord. So our second order neuron is going to be receiving the information from our sensory neuron and communicating it upward to our third order neuron, which is going to tell a synapse in the spot of our brain that's responsible for processing, and that's when we become aware. So the interesting thing is that depending on what type of receptor is activated will determine the arrangement here of the sensory neuron to the interneuron. So for some receptors, the sensory neuron is going to synapse right there on the second order interneuron, and then that interneuron is going to rise all the way up through the spinal cord and synapse on the third order neuron in the thalamus. Sometimes the sensory neuron is super long and it rises all the way to the brainstem before it synapses onto the interneuron, and the interneuron goes to the thalamus. So those are all details you can talk about in a neurophysiology class. We're just trying to get the basics of everything so that when you get to neurophysiology, you've seen this before. So our second order neuron, what we can say about that is it's either at the level of the spinal cord of our first order neuron or in the brainstem, and what it's doing is it's communicating information from that first order neuron to the third order neuron. It is an interneuron by functional classification, and it is a multipolar neuron by structural classification. So we'll say this is a multipolar interneuron. That brings info from our first order neuron to our third order neuron. Now, does anybody remember what the sensory relay station is? It's the thalamus in the diencephalon. So sensory information that's going to go somewhere in the cerebrum, with the exception of smell, has to go through the thalamus first. So that means that all of our third order neurons are arising from the thalamus and going to the part of the cerebrum that's responsible for that processing. So in the case of our somatic general sensory information from our body, that'll be the parietal lobes. For our third order neurons and our special senses are going to the occipital lobes or the temporal lobes. We'll go into that when we get to the special senses. But for now, what what we can be aware of, that is that either this interneuron that's arising from the spinal cord and all the way to the thalamus, or that's arising from the brainstem and going to the thalamus, that's the second order neuron that's going to end up in the thalamus where our third order neuron starts. So this is also an interneuron by functional classification, which is a little weird. It's wholly contained in the central nervous system, and it's a multipolar neuron by structural classification. So again, we could say for our third order neuron, this is going to be a multipolar interneuron. And its soma is in the thalamus, and its axon terminal, in the case of our general sensory information, is in the primary somatosensory cortex of the parietal lobe. So we'll say it originates in the thalamus and terminates in the primary sensory cortex, for whatever sense we're talking about. In this case, the somatosensory cortex, your primary visual cortex, your occipital lobe, primary olfactory and auditory cortex in your temporal lobe, primary gustatory cortex in your insula. So we'll just say it's going to synapse in the primary sensory cortex. This is yet another unknown effect of working in your living room. That your 4-year-old runs around your house making rocket ships from your expo markers, taking off the lids, and they all run out. Okay, so what if I was trying to draw a picture of this whole thing? Let's say I kind of got our receptor to our first order neuron to our second order neuron. How do I fit my third order neuron on top of there? I can't, I'm not tall enough. And if I draw it down here, it's like opposite how it works in the body. So let's just start, pause. All right, so let's think about this from the perspective of the body up to the brain, which is how books teach it, right? We're going in the reverse order from the brain down, and that's because the brain controls everything. So everything else you have to learn is controlled up here. So we're starting up here. Let's talk about these ascending tracts and this relay of information. So our first order neurons are going to be the sensory neurons that are in contact with some receptor. So receptors are detecting some change in the environment, and depending on what type of receptor is activated is going to determine what the anatomy of your first order neuron looks like. Either way, it's a unipolar sensory neuron that's bringing its information into the central nervous system. The question is it synapsing there at the level of the spinal cord onto the second order neuron, or is that first order neuron so ginormous, is it hooked up to a sensory receptor that is in a pathway where now our sensory neuron is going to arise all the way up to the brain stem and then synapse onto our second order neuron. So that's where we're going. And well, you don't have to worry about the nitty-gritty details of these pathways because you'll learn that stuff in a neurophysiology class if you have to. At least now you'll understand what an ascending tract is and kind of the way that our neurons work in a relay-like fashion to bring information up. So, all right. Our first order neurons are unipolar sensory neurons that are synapsing onto our second order neurons, which are multipolar interneurons totally contained in the CNS. So that sensory neuron will synapse there at the level of the spinal cord, and then the interneuron will decussate and cross over and bring the information up to our third order neuron. Our third order neuron now is going to be the one that's originating in the sensory relay station, the thalamus, and taking it to the part of the brain that's responsible for processing. In the case of our somatic senses from our body, that will be the postcentral gyrus or your primary somatosensory cortex. So I've drawn that in orange here. So either way, here's our first order neuron synapsing on second order neuron, or our first order neuron synapsing at the level of the brainstem on a second order neuron that then is going to arise to the thalamus and synapse onto our third order neuron. Third order neurons then are taking the information from the thalamus in the case of general senses to your primary somatic sensory cortex or the postcentral gyrus. Okay? So that is how sensory information ascends in tracts to your brain through an ascending tract. So the ascending tract is going through your spinal cord, right? To your brain. This stuff, the nerves, we're going to talk about next class. I don't know if I'm going to change. I'll probably just throw on a hat and we'll pretend it's a different day. Hopefully it'll be a different day for you. Okay. So now when we're going to execute motor commands, those are going to come down from the brain and come through the spinal cord in descending tracts. And the thing about descending tracts is that they either have 2 or 3 neurons. So all of our tracts have like 3 neurons. Descending tracts have 2, maybe 3, but we don't name the guy in the middle if there are 3. In a descending tract, we name the upper motor neuron and the lower motor neuron. And the weird thing about it is, our upper motor neuron, that's its name in the descending tract, but it's an interneuron that's totally encased in the central nervous system, originating in the where, if it's voluntary? Primary motor cortex, your precentral gyrus and your frontal lobe. And then it's descending to synapse onto a lower motor neuron that is now going to synapse onto your skeletal muscle so that you can move. Okay, so descending tracts now have 2 neurons, and we're not going to name the third one if there's a middle one. Just be aware that there might be a third unnamed interneuron in there. Our upper motor neuron is going to arise from the primary motor cortex and the precentral gyrus of the frontal lobe. So arises from, I'm just going to write down our primary motor cortex. And you're going to fill in all the rest. Why? Because you've read it, because I've said it, because you're memorizing it. Our upper motor neuron is arising from the primary motor cortex, which is in the precentral gyrus of our frontal lobes. So, my upper motor neuron is right here on the right side of my brain. Let's say it's originating. Which side of the body is going to move? My left, right? Because I decussate. I have ipsilateral control. Okay, so in my descending pathway, my upper motor neuron is going to leave and synapse onto my lower motor neuron. And now my lower motor neuron, we're just going to say that there might be an unnamed interneuron. But the one that I'm definitely naming is my lower motor neuron, and that is going to arise from the spinal cord in those ventral horns. For our muscles, our skeletal muscles we control in those ventral horns, we'll see our somas of our lower motor neurons that are then synapsing onto skeletal muscles. So for our lower motor neuron, we'll say that its soma is in the ventral horn, and our primary motor neuron then is synapsing onto our motor neuron, and the axon, we'll say, is going to terminate at a skeletal muscle. In the case of our somatic nervous system. In the case of our autonomic nervous system, we'll see we have a different kind of chain. We've got 3 neurons, preganglionic, and we're going to name them all. Preganglionic and postganglionic neuron. And for, what else was I talking about? Glands. That's, yeah, something totally different next semester. So the effectors of output are muscle and glands, right? Lower motor neurons we'll talk about this semester in great detail, where our lower motor neurons synapse onto skeletal muscles that's all of chapter 9, I believe. And then next semester we'll talk about what happens. Well, at the end of the semester we'll briefly review our autonomic nervous system and talk about it in great detail next semester. So that wraps up your introduction to the central nervous system, and I will see you soon for the peripheral nervous system. So I think most people, when they think of the brain, are thinking of only the cerebral hemispheres.